An application of redox chemistry is making a battery. A battery is also called a voltaic cell. So what we're going to do is look at a list of standard reduction potentials. Potential is just another word for voltage. So for example, here are two half reactions from a table of standard reduction potentials. Both of them are written as reductions. We could change them by switching the products and reactants around, and then our reduction would be an oxidation. Right now, the copper half reaction has a positive standard reduction potential. Superscript 0 means under standard conditions. The zinc has a negative standard reduction potential. The key is, if you're trying to make a battery out of this, you have to have a spontaneous reaction, because a battery is a power source, and you don't want your power source to be a non-spontaneous reaction, otherwise it's not an effective battery. We need to have one oxidation and one reduction. It's impossible for a chemical reaction to have two reductions. If I added together these two half reactions the way it's written, the electrons don't cancel, so you have to have one oxidation, one reduction. In other words, copper 2 plus can't react with zinc 2 plus. One of these two has to be switched. And the key to figure out which one is going to be switched is based on this equation. The standard voltage of the cell, or the battery, is the standard oxidation potential plus the standard reduction potential. When you flip a reduction into an oxidation, the standard voltage becomes the negative of whatever the standard voltage was. So one of these two half reactions will have to be switched into an oxidation to make this a battery. And the one we're going to switch is the one that's going to give us a spontaneous reaction. And we know a spontaneous reaction must have a positive voltage for the cell. So I have two choices. If I flip positive 0.34 and make it a negative 0.34, when I add it to negative 0.76, two negatives are going to give me an overall negative answer. So the one I have to flip is the zinc half reaction. I'm going to turn this half reaction into an oxidation, and when I do that, the voltage changes to a positive 0.76. Now when I add it to the positive reduction potential, a positive 0.34, my overall answer will be positive. In this example, I don't have to do this, but sometimes you have to multiply a half reaction in order to make the electrons cancel. This one was nice because two electrons will cancel two electrons once we flip the zinc. We don't have to multiply by any constant. If we did, a key point to keep in mind is that you never multiply a standard reduction potential or standard oxidation potential by anything, because a volt really has two units, joules per coulomb, and if you multiply the numerator by a factor, you're also multiplying the denominator by a factor, and the net result is the voltage does not change. So here I've rewritten the oxidation potential because I flipped the zinc half reaction around. Now I can add these two together. I make sure that the electrons lost and electrons gained are the same, so they're going to cancel. And I can calculate the voltage of this battery or cell by just adding together the reduction potential plus the oxidation potential, which gives me a positive 1.10 volts. The overall reaction for this battery is just the chemical reaction that we get. Copper 2 plus zinc turns into zinc 2 plus copper.